All right, let's talk about the ideal gas law. You've probably seen PV equals nRT 1,000 times, but today we're not just going to be plugging and chugging numbers. We're going to treat this equation like a master key, a single, powerful tool that we can actually reshape to build an entire toolbox for tackling some really cool, complex problems with gases.
So here's the game plan. We're going to start by really understanding our master key. Then we'll use it to forge 3 brand new tools. The first one, a gas identifier to figure out what an unknown gas is. Second, a mixture manager for when you've got more than one gas hanging out. And finally, a reaction calculator to figure out exactly how much stuff you're making. Let's get to it.
So first things first, let's take a closer look at that master key. PV equals nRT isn't just a formula to memorize, you know? It's a fundamental statement about how pressure, volume, amount, and temperature are all tied together for a gas. This single relationship is the bedrock for everything else we're going to do today.
And here it is, the star of our show. PV equals nRT. Pressure times volume equals N, the number of moles, times R, that trusty ideal gas constant, times temperature. Every single tool we build from here on out is going to come directly from rearranging or reinterpreting this one elegant equation. It's basically the Swiss Army knife of gas chemistry. Okay, master key in hand, let's build something. Tool number 1, the gas identifier. So picture this. You've got a mystery gas in a flask. You don't know what it is. How could you figure it out? Well, this tool is going to let us use its physical properties to uncover its chemical identity.
Now, we all know density is just mass over volume, right? But for gases, it's kind of tricky. You crank up the pressure, the density changes. You heat it up, the density changes again. So the real question is, how can we use our master key, the ideal gas law, to connect this ever-changing density to something that is constant for a gas, its molar mass, because that's the key to its identity.
This is where a little bit of algebra works like magic. We just take PV equals nRT and shuffle it around a bit. First, let's get moles per volume, or N over V, by itself. See? N over V equals P over RT. Now for the clever bit. We're going to multiply both sides by the molar mass, and check out what happens in step 4. Moles per volume times grams per mole. The moles cancel out, and you're left with grams per volume. And what's that? It's density.
And voila! Our first tool is complete. The density of a gas equals its pressure times its molar mass, all divided by R and T. What's so brilliant about this is that we've just created a direct link between a property we can easily measure in the lab, density, and a fundamental chemical property that's unique to every compound, its molar mass. This is exactly how we can identify that mystery gas.
All right, time to put this new tool to the test. Here's a classic problem. We've got the density, the temperature, and the pressure. All you've got to do is rearrange our new density formula to solve for the molar mass, that capital M. Plug in the numbers, carefully, and the answer you get should point you right to the identity of this gas. Go ahead, give it a shot.
Okay, great. So that works perfectly for a single pure gas. But let's be real, most of the time gases are mixed together. I mean, just think about the air you're breathing right now. It's a mixture. So what happens when you've got a bunch of different gases all bouncing around in the same container?
Here's the key idea, and it's kind of weird when you first think about it. As long as they don't chemically react with each other, the different gases in a mixture totally ignore each other. It's like each gas molecule is in its own little world, bouncing off the walls of the container as if it were the only gas in there. That means each gas exerts its own pressure, completely independent of whatever else is in the mix.
And this whole idea is summed up beautifully in what's called Dalton's law of partial pressures. It sounds complicated, but it's probably one of the simplest laws in chemistry. All it says is that the total pressure you measure is just the sum of the individual little pressures, the partial pressures, from each gas in the mix. P total is just P of gas A plus P of gas B plus P of gas C, and so on. That's it.
A perfect example of this in action is a really common lab technique, collecting gas over water. When you bubble the gas you made in a reaction through water into a container, that container doesn't just have your product gas in it. It's also got water vapor mixed in. So the total pressure you measure is actually the pressure of your gas plus the pressure of that pesky water vapor. To figure out how much product you really made, you have to find its pressure alone. So, how do we do that? It's a super simple 3-step fix. First, you just measure the total pressure in your collection flask. Second, you look up a known value, the vapor pressure of water at the exact temperature of your experiment. And third, you just subtract the water pressure from the total. What's left over is the pure, dry pressure of the gas you actually made.
And now, it's time for our final and maybe most powerful tool. We're going to bring everything together to answer the biggest question in chemistry: how much? We're talking about gas stoichiometry, the science of calculating the exact amounts of gases you use or produce in a chemical reaction.
The secret that unlocks this whole process comes from our old friend Avogadro. This law is huge. Think about what it's saying. If the temperature and pressure are the same, the volume of a gas is a direct stand-in for the number of moles. This gives us a massive, massive shortcut when we're dealing with reactions that involve only gases.
So what does that mean in practice? It means we can look at the coefficients, the big numbers in front of the molecules in a balanced equation, and read them not just as a ratio of moles, but as a ratio of volumes. We can go straight from liters of one gas to liters of another without ever having to touch a mole calculation.
Let's make this real. Think about burning propane in a gas grill. The balanced equation has a 1 in front of the propane and a 5 in front of the oxygen. Because of Avogadro's law, that means that 1 liter of propane gas needs exactly 5 liters of oxygen gas to burn completely. So if you've got 2.7 liters of propane, a quick calculation tells you you're going to need 13.5 liters of oxygen. It is that simple and direct. But what if you're starting with a solid reactant, not a gas? No problem at all. We just build a little roadmap. You start with the mass of your reactant in grams, convert that to moles. Then you use the mole ratio from your balanced equation to find out how many moles of gas product you'll make. And for the grand finale, you use our master key, PV equals nRT, to turn those moles of gas into a final volume.
And just like that, we're done. By starting with just one fundamental law, we've managed to build an incredibly powerful and versatile toolkit that helps us understand, predict, and calculate pretty much anything we need to know about gases. So let's lay everything out on the workbench. We built the gas identifier, which uses density to unmask a mystery gas. We added the mixture manager, using Dalton's law to untangle the pressures in a gas mixture. And finally, we constructed the reaction calculator, our powerhouse tool for figuring out the how much in any gas reaction.
So at the end of the day, this is about more than just a bunch of formulas. It's a way of thinking. These tools let us connect what's happening with individual, invisible gas molecules to huge, real-world outcomes. So I'll leave you with a final thought. How do these simple rules governing these tiny little particles scale up so much that they allow us to manufacture fertilizer to feed billions of people, or even model the future of our entire planet's climate?